We want to look at how can we write the variance formula, which is given to us as expected value of x minus expected value of x whole square and expected value of x squared minus expected value of x whole square. So we want to use this form of variance to prove this form of the variance formula. So for this, let's start off with the formula. We know variance of x is equal to, we can write this as expected value of x minus mu whole square. Now what is the mu over here? So mu is essentially just expected value of x. So instead of writing expected value of x, I'm just representing it by mu, the mean value of x. And this is essentially a constant because remember when you take expectation of a random variable, what we get is a constant, right? So just keep in mind mu is expected value of x, which is just a constant. Now the first thing that we'll do is that, we will expand, right? So the first thing that you're going to do is we will expand x minus mu whole square using a minus b whole square. Now what is a minus b whole square? We know this is a square plus b square minus 2ab. So using this identity, we will first expand what we have inside expectation side. So this will become the variance of x is equal to expected value, and this will become x square plus this would become mu square, right? We're just applying this identity minus 2x times mu, right? This is what we've applied here. Now we'll use the fact that expectation is a linear operator. Since expectation is a linear operator. Now, what do we mean by linear? Now, linearity means that expectation operator can go inside summations. So expectation operator can go inside summations and constant multiples can come out. This is what linearity means. Can come out. So what this essentially means is that it can go inside summations, which means that the expected value of x plus y is just expected value of x plus expected value of y. And constant multiples can come out means the expected value of ax would just be a expected value of x. So this is what we mean by linearity. It can go inside summations and constant multiples can come out. So to keeping this in mind, we can write variance of x, so it can go inside summation. So we can write expected value sum is sum of expectation. So expectation is that which is sum of expectation plus expected value of mu square minus 2 expected value mu x. Right, so what we've done is we've taken expectation inside the sum. The expectation of sum is just the sum of expectations and 2 is a constant multiple which we've taken out because expectation is a linear operator. Here, that's the reason why we expanded x minus mu square using a minus b square because linearity does not allow it to go inside non-linear functions like squares, right? Like it's not true that we could have just taken this directly inside the square. That's not possible. Linearity only allows it to go inside summations and for constant multiples to come out. So that is the reason we needed to expand x minus mu square so that then we can take expectation inside the sum. Here, directly expectation cannot go inside the square. That's not what linearity allows, right? So just a warning, let's just quickly do it. A warning, this is not true. Expected value of x minus mu whole square is not equal to, right? It's not possible that expectation, this is not true, right? You could not have taken the expectation directly inside the square. That's not possible. Linearity does not allow it to go inside non-linear functions like squares. It can only go inside summations. That's why we expanded it and constant multiples can come out. Right? So this is not true. Right? It cannot directly go inside the square. Right? So we have this. Now over here now, something to note here is we know like we established mu is a constant, right? Mu is a constant. So mu square is also a constant. Obviously, if mu is a constant, then its square is also a constant. And expected value of constant is equal to that constant. right? So here we know the answer, this is just mu square because we already established that mu is a constant, so its square is also a constant, and expected value of constant is just a constant. Here also we have a mu. Like we said, mu is also a constant, right? Like 2, mu is also a constant, and we know expectation is a linear operator, and any constant multiples can come outside. Just like the 2 we brought outside of expectation, we can do the same with mu. So can take this outside expectation as well, like 2. So can take this outside expectation as well. So if I do that, then this will become variance of x is equal to expected value of x square plus this becomes mu square, right? Because like you said, mu is a constant, so mu square is a constant, and expected value of this constant mu square is just the constant mu square itself. And just like we brought the 2 outside of expectation, the mu can also be brought outside the expectation, right? Because any constant multiples can come outside expectation. And because mu is a constant like 2, we could have written this outside expectation as well. I just clear this up. Let's just clear this up. And so this is what I've written so far. Let's just write this again. So this is what I've written so far. Okay, variance of x is equal to expected value of x squared plus mu squared minus 2 mu expected value of x, right? This is what I've written so far. Now, this mu over here, right? If I just sorry, if I just write it like this mu over here is just what? This is expected value of x, right? So basically, this is just expected value of x. Because remember, we took mu is equal to expected value of x. We said mu is just equal to expected value of x. So instead of mu, I can just replace this back with expected value of x. I can write this as expected value of x. So I can write this as expected value of x squared plus expected value of x whole square, and this also becomes sorry, not mu, so it's mu is just expected value of x, so this is expected value of x times expected value of x, so this is also expected value of x whole square, because this is also expected value of x, this is also expected value of x, so we're multiplying them, so it's a square. And now this can just be shown as expected value of x squared. So this will just become minus expected value of x whole square. So we have shown that variance of x can also be written in this form, right? As expected value of x square minus expected value of x whole square.